Attention is all you need. Part 8. Results. Proof of performance. Now comes the moment of truth. We've seen the architecture and understood the training regime, but does it actually work? Let's look at the results that made this paper legendary. The authors tested the transformer on two major translation benchmarks. On the WMT 2014 English to German translation, the big transformer achieved 28.4 blue, improving over previous best results including ensembles by more than 2 blue points. In machine translation, improvements are typically measured in tenths of a point, so jumping ahead by more than 2 is massive. Training time? Just 3.5 days on 8P100 GPUs. On the English to French translation task, the big transformer hit 41.8 blue, achieving the best performance, even compared to the top ensembles. Same training time, 3.5 days on 8 GPUs. But the training cost was less than 1/4 of previous state-of-the-art models. Better results for dramatically less computational expense. How did this stack up against the competition? For English to German translation, previous models ranged from ByteNet at 23.75 blue, with the best ensembles reaching around 26.3. The base transformer, the smaller version, hit 27.3, beating all previous single models and ensembles. The big transformer reached 28.4. For English to French translation, the best models at that time ranged from deep attention at 39.2 through convolutional sequence-to-sequence, or ConVS2S, and others around 40.5, with top ensembles reaching 41.3. The big transformer's 41.8 moved past even those ensembles, while remaining a single model trained in a fraction of the time. Now here's where it gets really interesting. The authors ran ablation studies. That is, they systematically varied different components to see what actually matters and what doesn't. They started with a base configuration, 6 layers, model dimension of 512, feed-forward dimension of 2048, 8 attention heads with key and value dimensions of 64 each, 0.1 dropout, 0.1 label smoothing, trained for 100,000 steps. This achieved 25.8 blue on the development set with 65 million parameters. Then they started experimenting. Attention heads proved crucial, but with diminishing returns. Dropping from 8 heads to 1 hurt performance significantly. Blue fell to 24.9. With 4 heads, it recovered somewhat to 25.5. Increasing to 16 heads matched the base model at 25.8, but pushing further to 32 heads with smaller dimensions actually hurt performance, dropping to 25.4. The sweet spot sits around 8 to 16 heads. Too few heads limits the model's ability to capture different relationship types, but too many heads means you have to make each one smaller to fit within the same total capacity, and that weakens each individual head. It's like dividing a pizza into too many slices. Each piece becomes too small to be useful. Model capacity showed a similar pattern. Halving the model dimension to 256 hurt performance, dropping blue to 24.8. Doubling to 1024 improved things slightly. But it came with a big jump in parameters, so the gains aren't free. Even the key dimension mattered. Reducing it from 64 to 16 dropped blue to 25.1. The model needs sufficient dimensionality to represent relationships effectively. The regularization techniques both proved essential. Without dropout, blue fell to 24.6, clear overfitting. Higher dropout at 0.2 reached 25.5. The base setting of 0.1 hit the optimal balance for this configuration. Label smoothing revealed an interesting trade-off. Without it, perplexity dropped to 4.67, but blue fell to 25.3. The model became more confident, but generalized slightly worse. Exactly what label smoothing is designed to prevent. For the positional encoding choice, learned embeddings scored 25.7 blue, and sinusoidal scored 25.8. Nearly identical, validating the sinusoidal choice with its extrapolation advantages. The big model configuration shows how to scale effectively. It keeps 6 layers, but doubles the model dimension to 1024, feed-forward dimension to 4096, and heads to 16, while maintaining key and value dimensions at 64. Crucially, dropout increases to 0.3 for the added capacity, and training extends to 300,000 steps. Result: 26.4 blue on the development set with 213 million parameters, achieving 28.4 blue on the test set. The pattern is clear. Bigger models work when you pair increased capacity with appropriate regularization and training. To test generalization beyond translation, the authors tried English constituency parsing, understanding grammatical structure, completely different from translation. The dataset was the Wall Street Journal portion of Penn Treebank, a standard dataset from the University of Pennsylvania. About 40,000 training sentences, much less data than translation tasks. Training only on this limited data, previous models achieved an F1 score of 91 to 93%. The 4-layer transformer hit 91.3% F1, competitive with minimal tuning. With semi-supervised training adding more data, recurrent models ranged from 92.1 to 93.0% F1. The transformer reached 92.7% F1, closing the gap with specialized parsers. This proves the architecture isn't just a translation model. It's a general-purpose sequence architecture that adapts to diverse tasks. So what do all these results tell us? First, architectural choices have optimal ranges. 8 attention heads consistently outperform 1, performing similarly to 16. The 512-dimensional base model is well-balanced. Dropout and label smoothing are essential, not optional. Second, scaling works with the right approach. The big models doubled dimensions and 16 heads deliver gains, but only with increased dropout from 0.1 to 0.3 and tripled training steps. You can't just add parameters and expect improvement. Third, efficiency gains are real and practical. The transformer achieves better results at a fraction of the computational cost. This isn't theoretical. It's measured in actual flops. That's FLOPS, which stands for floating point operations, and in real training time. Fourth, the architecture generalizes. It excels at translation, its design target. It competes on parsing, a different task with limited data. This suggests broad applicability. Fifth, every design choice has evidence. Multi-head attention validated through ablations. Positional encoding works whether learned or sinusoidal. Model dimensions show clear optimal ranges. Regularization techniques both contribute meaningfully. These aren't just impressive numbers. They're comprehensive proof the transformer delivers on every promise from the paper's opening. The authors claimed an architecture based solely on attention would be more parallelizable, require less training time, and achieve better results. The results prove all three. State-of-the-art translation performance, training in a fraction of the time, and generalization to other tasks, all confirmed. This is what makes compelling research. Bold claims backed by thorough validation. They proved that attention really could be all you need. That recurrence and convolution, the dominant paradigms researchers had relied on for years, could be set aside entirely. The step-by-step processing that seemed fundamental to sequence modeling? Not necessary. The convolutional approaches that had just started gaining traction? Superseded. The transformer showed a new path. Let every position attend to every other position directly. Process everything in parallel where possible, and trust attention to handle the relationships. And the efficiency gains made it practical. Previous state-of-the-art models required weeks of training on expensive hardware. The transformer achieved better results in days, at a quarter of the computational cost. The parsing results sealed the deal. If the architecture only worked for translation, it would still be significant. But demonstrating strong performance on a completely different task with limited data suggested something bigger: a general-purpose architecture for sequence modeling. The ablation studies gave practitioners a roadmap. Want to build your own transformer? Here's what matters. 8 to 16 attention heads work best. Use appropriate dropout for your model size. Label smoothing helps. Don't just scale up blindly. Match increased capacity with stronger regularization and more training. This level of thoroughness, not just showing the architecture works, but explaining why each component matters and how they interact, made the paper immediately actionable. The ripple effects are still unfolding. BERT, GPT, T5, and essentially every major language model since 2017 builds on this foundation. The transformer architecture became the default choice for sequence modeling across domains. Not just translation, but text generation, question answering, summarization, and code generation, even extending beyond NLP into vision and other modalities. Coming up in Part 9, we'll wrap up with the author's final thoughts and connect these technical achievements to the revolution they sparked in AI.